Hello, welcome back to our tutorial series on designing the BJT based circuits. And on your screen, you see you have this common emitter amplifier with a little modification to the previous circuit that we have seen. So the circuit earlier was something like this. Let me show you. Here is your circuit. If you see that you have this emitter resistor, the collector resistor RC with a connected one end connected to the power supply V plus. We have a 5 volt voltage source here. Now we have a transistor BC547, and then to the base of it is has 0.7 volt. Emitter is grounded. Output is taken from the collector. So that's the basic version of common emitter mode transistor, NPN transistor configured in CE mode. However, there was a drawback of this circuit. For example, we saw initially the gain, which is a ratio of VO over V in, is equal to GM times RC, where GM is the transconductance of the amplifier, and the value of it is IC over VBE, which with VCE is equal to 0. Right, so IC is the DC biasing current of the transistor, and the VB is small signal AC voltage. So we see that the gain is dependent on the intrinsic parameters such as the transconductance of the circuit, and there was some the circuit is said to be having a limited dynamic range, because if you try to exceed that one, then the output exhibits distortion, and there was a stability issue as well. So to fix this, what we did here is we are with this new circuit, the same circuit essentially, but little modification. Instead of tying the emitter directly to the ground, we connect it to the ground through this resistor RE. Rest of the circuit is pretty same. So you have emitter, you have base, you have collector, and this transistor is NPN, NPN. Okay, and now the gain, this is for the gain for this earlier version of the circuit. For this circuit, your gain is essentially GM times RC divided by 1 plus GM times RE. Yeah, and assuming that GM times RE is very, very greater than 1, this then approximates to GM times RC divided by GM times RE, which is equal to RC over RE. So if you compare this value of a gain with this value, we see that the gain is set for this circuit. For this circuit, the gain is set by a ratio of resistors RC and RE. That's it. There is no, the gain is no more dependent on the transconductance GM of a transistor. Okay. And before that, let me give you the value of GM also. There is one equation like this, and there is another equation. So let me share with you that uh, it is also GM is also expressed as IC over VT, where IC is the quiescent value of the collector current, and the VT is the thermal voltage. And thermal voltage is 25 millivolt at the room temperature, actually. So we have this condition, and this IC essentially is a small IC because we are talking about the AC model of the circuit. So let me write it properly. GM. Okay, GM is small IC over small VB with VC equal to 0, and this is your DC value of a 0. Okay, so we got the two expression for the, this was for the previous circuit and this gain expression for this circuit. Now let us analyze this circuit. What we see here, you have a positive voltage source which is of 5 volt connected to the one end of the RC. Value of RC is 100, value of RE is 10. So if we go by a theory calculation, our gain is basically will be 100 by 10. RC is 100, RE is 100. So that's the value of 10. And take a 20 log of 10 would be like 20 dB. Yeah, we'll see that in dB. We'll have that. So when we simulate the AC response, we should have this one. We'll see that. Okay, and remember, I have taken the magnitude, the mod of the magnitude. Therefore, I am not putting the negative sign here. So um, the otherwise it is a CE, common emitter configuration. So the output will be inverted or 180-degree phase shifted to the input signal. Now the bias point of this circuit will be set by these voltage sources that you have given to the supply, and especially this input voltage. So input voltage is V in, and the net the voltage at this node is VB, for example. The name of the source is V in 1, and the net name of this wire is VB. And I want to say that this is the 0.7 volt here at this node. And what is the voltage here that one needs to determine? So it will be, if you apply the KVL in this loop, let me show, it will be V in 1 minus VBE minus IERE is equal to 0. So IERE is the drop of your voltage source. If the is the drop across the resistor RE, which is VE, this voltage will be equal to V in 1 minus VBE. So V in 1 is 7 minus V in 1 is the 0.7 volt what we apply, and VB will be approximately 0.6 volt. So it should be about 0.1 volt. Depends, assuming that drop. Okay. Now let me fix it. Just a minute. We'll check this out, how we can actually run before we run the simulation. So that's good. We have done some theory calculation. Now, how about the transistor? If we simulate the circuit, before that we should know the properties of a transistor. What I do, I will right click this transistor and try to see what transistor I have chosen. So it is BC547C. You can open Google and try this number to access the data sheet. And this is from the manufacturer NXP. It's NPN. The maximum voltage across is collector to emitter junction, or we'll say that the open circuit voltage across collector to emitter, it can withstand is 45 volt, and maximum current flowing through the collector terminal is 100 milliampere. So we have to be in limit. Now, let's say I click here and I see these spice model for this specific transistor, and I see that these two values 45 volt 100, and then comes the spice model with the syntax dot model. Here I see various parameters such as IS, reverse saturation current, for example, but mainly I am concerned about the beta factor BF, which is 558.7, approximately 450, 458.7 actually. And other parameters also there, but we don't really give it attention. So cancel, click OK. So we know that the beta of this transistor let's say we'll write here is about 458.7, okay, or 5.5 or something. With that said, if we know the value of IB, we can multiply it with this beta factor to get the value of IC. Okay. And output voltage through this expression, because we can also say that we know that this is 5 volt. So what we'll see, we'll write the expression for the output, which is V plus minus ICRC. So which is 5 minus IC times 100 is the RC value. So we need to know the value of IC. Second expression for the VO is simply VCE, which is the drop across this, VCE minus VE. VE is this voltage, or IRE. So it is like you should know what is IRE. So IRE is roughly we calculated to be 0.1 volt. But remember, we just assumed the value of VBE. We don't know what is the value of VBE here. Do we have that in our SPICE model? Let's check. Because if that is the case, it's easier for us to understand and calculate it in a simple way. So VBE, do we have the value of VBE in any? Is NF, IAC, NE, beta factor, VAF, NR, ISC, NC, BR, IKR, VAR. Then what else? There are actually many things here. Capacitances and all those things are there, but to nowhere we see if we have access to the VBE. Here, VCEO 45, I crafting manufacturer, CGS, CGC, VGC. Not really, we don't really have access to that, but so we need to rely, we assume that, we can assume it is 0.6 or 0.65. And then input voltage is V in is so let's better way is to simulate and see the operating point. So assuming VE is about 0.1 volt, so VCE, we don't know what VCE is, so we don't really know. So it will be like VC minus VE. Oh, no, 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 no. The output voltage will be VC uh, minus VE, not the VCE. So it would be VC minus VE. Right, at this node. So this voltage. Okay. So why not just run the AC operating point analysis? So here is that command that we have done. I am not going to explain you how I put this command here, because you refer to the other previous videos. We have so many videos explaining that how to use SPICE. So let's do that. So what I'll do, I'll run the simulation, click, and now you see output voltage is 4.5 volt. 4.5 volt. So it's like you have, and then this is your input voltage. That is something you apply, that is 0.7 volt. Then you have VE, this is 0.041, that is the drop that we actually got. It's pretty small, 0.04, that is the voltage at this node. And then this is a V plus, that is a voltage power supply. Then the collector current is your 4 milliampere, 4.1 milliampere. So let's say IC is your 4.1 milliampere. Then you have base current, that is IB, is your 8.6 microampere. So it's about beta factor approximately 500, which is what we see in the SPICE model. It was 458. You see in the screen. Let me show you that we have written it before, this beta factor. Look, and this is pretty close to, not exact, but is still close to what we see here through calculations. Now, next is your emitter current. Then current through RC is same, which is collector current. Current through RE is approximately same, neglecting the base current. IC and I will be same. And then you have the current from the input to the base. And then you have the current from the input to the base, and this is a current from your supply voltage source V1. This is the power supply. So what we understand from this is two things. We know that in order to work this circuit as an amplifier, we should bias it in an active region. Active region means the base emitter junction should be forward bias, so which is like 0.7 volt right here, minus voltage at VE. Voltage at VE is 0.04 volt. So you see, it's pretty small. So approximately is like 6.96 volt is the VBE. Okay, 6.96 volt. And let me just take it here. Okay. Okay, so we'll just say that this is our VBE. And then what else to be noticed? So base emitter junction is forward bias, base is positive with respect to emitter, and then base collector junction is reverse bias. So the voltage at the collector, which is your VO, is 4.58, and the voltage at the base is 0.7. So it's like there is a difference about VBC, which is negative of like 3.58, so 3.51. Okay, or 4.51 minus 4.51. So that's our reverse biasing condition to that. How about we run the transient simulation now? We'll see that. So close this, and maybe we'll simulate, then edit simulation card. We'll run the transient. Transient simulation will be like stop time, let's say 10. Oh, before that, I forgot. We need to check the voltage source. So here is the voltage source. Right click. We don't need a DC voltage source now because we are running the transient analysis. And before that, let me get rid of all this drawing, because that's the better way to understand the circuits. Remember all these things. Now we need to click the advanced, and we'll select the sine wave. DC offset. What is the DC offset? We have kept the DC offset 0.7 volt. So we have to keep it 0.7 volt. Because if we don't do that, then we are not biasing the transistor. We need to have the AC voltage greater than 0.7 volt. So this is just to DC bias the transistor. Then let's say 1 millivolt, or let's say 10 millivolt. Frequency is 1 kilohertz. Rest will skip 10 cycles. That's it. So let's say you have like, this is your command. Then you do the transient analysis. Edit simulation card, choose transient, stop time, let's say 10 millisecond. Then you choose to save data from 0 second maximum, let's say 1 millisecond. So your command is ready, put it here. That's it. As soon as you select the transient analysis, your operating point analysis, previous analysis got disabled with this comma run. Fine. So this is our previous circuit. We don't want that for a moment. Let's tile the windows and now input on the schematic, the red probe. Click, you got this waveform. See, your waveform starts from 700 millivolt, which is your DC biasing point of operating the transistor as an amplifier. Then you got this 700 milliampere here. And after that, you have on top of that, you have a 10 millivolt peak, a sinusoidal waveform riding on it. So 10 millivolt up, and then from 7 millivolt again down 10 millivolt. Again come to 700 millivolt, again 10 millivolt up, come back to 700 millivolt, down 10 millivolt. So 690 to 710, you have an input voltage swing, which is what we expect. And now time for output. Now what is output? Output was about 4 point something. So it will have that DC line, DC voltage level, and on top of that will be riding the sinusoidal output. So you got that. See, exactly 4.5 was that DC level, and on that you have. Now how much is the gain? RC divided by RE was our gain. So gain of 10. So if you apply 1 millivolt as an input, you should have 10 millivolt in the output beside the DC level. So we are not able to see the output properly. What I'll do on the waveform, I right click, I add a plot pane, and then maybe one of the waveform, I take it in different one. So input, now look, the output is like 4.59 and it goes to 4.52. So how much is the gain? Or maybe just right here 4.48 to 4.54. Yeah, like we expect, like if we apply 10 millivolt, then the gain of 10 should give us 100 millivolt. So let's do that. Zoom to fit. Let's maximize it. So here we are 4.58 something, and then zoom to fit. We go down 4.53. So how much is that? 58 to 53. Yeah, so it's like for 10 millivolt, 4.53. Right click and maybe let me do this. Draw, edit, file, add trace now, auto range y-axis. So how much is the gain? 4.5864. So it's about 60 to 65 millivolts. So about 6.5 times the gain. And theoretically, we calculate about 10 times, right? So there is this difference, but you see the phase is inverted. You have positive and negative here. You have negative and also output is inverted because that's the common mode, common emitter mode, 180-degree phase shift. Having said that, now what about plotting the collector current? So you just take a look at it here. So you have like collector current IRC that varies from bias current is 4.2 milliampere, and then it is also your gain is 4.8. So zero point 0.6 milliampere is your gain, like 6 times. What about IB, the base current? Can you plot that? So this will be the base current here. Now B in. So all the current and voltages, similarly current through RE and current through RC. So all these things you can plot, and that's how you will learn to analyze your signal. So hope you understood and like this video. If you did so, do share with others, comment on the video, and stay tuned for wider reach. Wish you happy learning.